Hello students, now we will start factor affecting chemical shift, the next topic on the NMR spectroscope. So first, we just go through the chemical shift. So what is meant by the chemical shift? It is a position of a specific signal from the TMS. So you can define as a difference between the absorption position of a proton and the absorption position of a reference compound is known as the chemical shift of that particular proton. Means consider your TMS, that is a tetramethylcellene, is your reference compound. As it is having the same magnetically environment of a CH3, that is 4 CH3, which is having the same magnetic field. So ultimately it will give you the signal at a 0, that is TMS. So this is your reference compound, and consider your compound is ethanol. So ultimately it will give you a signal like CH3, CH2, OH, because the signal which is receiving NMR spectroscopy is with respect to the proton, that is of hydrogen. So ultimately your ethanol compound is CH3, CH2 and OH. So the CH3 will give you some signal, CH2 will give you another signal, and OH is another signal with respect to the TMS. So consider this signal you receive by your ethanol. So you can say the delta value or the chemical shift of this CH3 is approximately 1 or 1.2, because the distance from the TMS is 1 or 1.2. Likewise, the CH2 also gives the signal here, so you can say it is at 3.5. So 3.5 is a chemical shift in case of the CH2 with respect to the TMS. Like if TMS का 0 है, so it will be a 3.5, and it will be a 4.8 or approximately 5, we can say, of OH. So by using the chemical shift, we can differentiate the position of a hydrogen atom in a particular structure, as well as it helps us to know the nature of a proton, like aromatic proton, aliphatic proton, or adjacent electron withdrawing group. Means if the any electronegativity group is attached to the hydrogen, then the position of a hydrogen may shift, or we can say the chemical shift value will change. So the chemical shift value is measured in the unit as a ppm. So we can say here the CH3 ka chemical shift is 1.1 ppm, CH2 ka chemical shift is 3.5 ppm, and OH ka chemical shift is around 4.8 or 5 ppm. So the you can say the denomination of chemical shift is delta value, and the unit for measurement is ppm. Next is your proton in a molecule. So consider this is your one molecule. Depending on the chemical environment, proton in a molecule are shielded by the different amount. So the shielding and de-shielding pattern we already seen in last lecture. So the link is provided in the description box, so you can go through it. So we can say that these three protons are more shielded. What is mean by shielded? When the induced magnetic field and external magnetic field is in opposite direction. So the induced magnetic field by this proton get cancelled or nullified by the external magnetic field. So we can say it is a more protected from the external magnetic field, because the if 1.14 Tesla magnetic field is applied externally, so the induced magnetic field cancel the power of external magnetic field. So ultimately the energy which may receive from the external magnetic field will not be the same. This external magnetic field का अगर power ज़्यादा है, that will be nullified by your induced magnetic field. So you can say your proton is get shielded or protected. So the proton which is here is more shielded or absorb at higher energy. So why it absorb at a high energy? Consider ये proton का induced magnetic field है, and you are going to apply the external magnetic field. इसके proton इसके बाजू इसके electron है जो ये proton के, that will be present in surrounding environment. So it will protect your proton, or you can say shielded that proton. So the magnetic field which is experienced by your that is proton, that is experienced by the external magnetic field, will be the less. so it is absorbed at a higher field. So the amount of magnetic field required for your proton to come in a resonance, it will be high, because the amount which is going to be applied externally, when some of energy will be nullified by the induced magnetic field. So ultimately we have to supply the more strong magnetic field, so then some amount get nullify, and we get the required amount of a magnetic field which is required to your proton come in the resonance. Okay. So it is a more shielded है मतलब protected है. So इसके protection को break करने के लिए भी थोड़ा बहुत amount of energy लगेगा. So we should provide a higher magnetic field that is of required magnetic field. So then the extra वाला magnetic field का energy will be used for nullifying this effect or nullifying this protection around the proton. So we can get a exact resonance frequency of that of the proton. And this is a less shielded or absorbed at a lower field. So this proton is a less shielded, means it is not covered with the electron. So it can be easily come into the resonance with the external magnetic field. So it can be absorbed at a lower frequency because it requires a very less amount of energy. Because no energy is required for breaking up this shielding or building of that protection cover. So we require very small amount of a magnetic field to bring this proton in a resonance. So we can say if the proton is more shielded, means protected with high electron density, then it will be you can say seen at a higher field or up field in your chemical shift value, or in a magnetic field. Means up field means towards TMS, because it requires a high amount of magnetic field, and less shielded or it get absorbed at a lower field, and you can see the delta will be as a down field. We can see here, so this is your molecule. So this 4 protons is there. Out of 4, there 1, 2, 3 protons are more shielded, so it requires a high field to come in a resonance, and it can be detected as a up field, means towards the TMS. So this is your TMS. These 3 protons are a shielded protons, that is a protected protons. So it requires a high magnetic field to come in a resonance. Therefore, it is detected as a upfield. Upfield means towards TMS. And this proton is a less shielded, means the electron density around this proton is very less. So it will be detected as a lower field or down field, means the amount of a magnetic field required for this proton to come in a resonance is very low. And you can say it is detected at a down field with a you can say high delta value, because this is 0. So ultimately consider this is your nearest to TMS, and as you go far from the TMS, the delta value increases. So you can see here, if the compound is if the proton is a more shielded, then it will be detected as a upfield towards TMS. If your proton is less shielded, then it is detected towards the downfield with a more delta value. So we can roughly say more shielded, high field towards TMS, less delta value. Less shielded, lower field away from the TMS, and high delta value. Because you go like this, the delta value is increased. Here it is a 0, and here it is a 10. So as your proton is shielded, it will towards the TMS. As the shielding decreases, it will move away from the TMS, and your delta values increases. So the main topic is factor affecting the chemical shift. So this is the 4 main factors that are going to affect the chemical shift. First is the electronegativity and inductive effect, hydrogen bonding, van der Waals shielding, and anisotropic effect. So anisotropic effect and van der Waals shielding is also there in first previous lecture. So you can go through that video also. So first we start with the electronegativity and inductive effect. So in electronegativity, we can say consider your Cl is a high electronegative compound. So it will pull all the electron towards itself. So consider we are interested to note down the signal of this proton, and if the chlorine is not there, only C and H is there. So the sigma electron which is present in this bond is shared between these two atoms, and the chemical shift received is on something delta value. If we add chlorine in another position, so ultimately when chlorine is there in this group, it will pull all the electron towards itself. As it pulls the all electron towards itself, the density of an electron towards the proton decreases. As the electron density decreases, the protection which is there around the proton is also decreases. Means we can say in absence of a chlorine, proton is protected, that is a shielded. As the chlorine is there, chlorine pull all the electron density towards itself. As electron goes towards the chlorine, the shielded proton is come into the de-shielded category because the electron is gone towards the chlorine. So there is no electron around this proton. So this proton is a after addition of chlorine, this proton is a de-shielded. So we can say the de-shielded proton appear at a downfield and with a higher delta value, and higher shielded proton appear at a upfield with a low delta value. So by using this slide, we can see that if it is a more shielded, it is upfield and lower delta value, and as the de-shielding, you can go towards the de-shielding, your delta value is increases. Same like this. So coming to the next example, like here fluorine is there, or fluorine, oxygen, fluorine, bromine. So it is a element, you can say, and the electronegativity is also there of that particular element. So we can know, we also know that the fluorine is a high electronegativity compound. So it will having the electronegativity high like a 4. So we consider this fluorine with a 4 value and consider bromine with 2.8. So we can observe the electronegativity of both. Fluorine is high electronegative and bromine is a less electronegative. So the power of electronegativity, we can simply say is the power of pulling the electron towards itself. So we can say if we compare a fluorine and bromine with each other, fluorine will pull more electron towards itself and bromine pull more electron towards itself, but a less power than that of the fluorine. So we can observe the de-shielding pattern also, because the hydrogen, which is absence of a proton, is protected or shielded. After addition of an electronegativity group like fluorine, the proton which is shielded previously undergo the de-shielding due to the electron move towards the fluorine. So it will be a 4.26. We observe the delta value 4.26, and the bromine value, when we add bromine, the delta value is 2.68. So we can see the more electronegativity group or more strong electronegativity group, then the delta value is high. If the somewhat less electronegativity group, then the delta value is lesser. Then next is the substitution effect of chemical shift. So here we can observe that first CHCl3 is there. Then we replace the chlorine is a high electronegativity group. So we replace one chlorine with a hydrogen. So ultimately it is a CH2Cl2. And then again we remove one chlorine, then it is CH3Cl. So we can say here the more chlorine is there, here somewhat less, and here some very less chlorine is there. So we can observe the delta value then. As the chlorine that is a high electronegativity group amount is decreases, your delta values decreases, because the chlorine is a major group which de-shield your proton. So simply we observe like CH, CH2 or CH3. In 3 cases only CH sigma bond is there and electron is around the proton only, which is in shielded position. As we add one chlorine group, then the delta value is shifted to the 3.0. As we add one more chlorine group like Cl2, or it will all shift to the delta value. Means your delta value of TMS से दूर जा रहा है, that means you are going to be a downfield. So you can say when you are going to add more chlorine atom, your delta value shifts from the TMS to the downfield, or you can say delta value increases. So the effect increases with a greater number of electronegative atoms. So the substitution effect, you can say, if we substitute more electronegativity group, more de-shielding will be observed and the delta value will be the more. Because we know the shielded रहेगा, so it will be towards TMS or less delta value. अगर de-shielded है, तो it will be go away from the TMS at a high delta value. So we can observe here, it is more de-shielded and it is also most de-shielded like a bromine. So here CH2 Br2 is there. Then we add one chain with of a bromine with a CH2. Here or more CH2 with bromine. So here also we can observe if it is there, we consider this proton is CH2. So here we observe when Br, that is bromine, is directly connected with the CH2, then the delta value is 3.30. As the position of electronegativity group is away from two bond or from one certain atom is there between that two, so the delta value get affected. Here the chlorine is directly attached to the proton. We are interested in the signal of this proton. So in 3 of case the chlorine is directly attached to the proton. But this phenomena is observed, like delta value is increases due to the shielding. But the position of electronegativity group is also important. Likewise, this proton is directly connected. So here also your bromine is directly connected to this proton to this delta value. As the bromine go away from the proton which we are going to interest in. Means consider this CH2. This CH2 is directly connected with the bromine. So this H2 proton will give you this delta value only. But if the hydrogen which is away or from a certain distance from the bromine, then it will give you this delta value. As it will go again away from the bromine, the delta value is decreases. So we can say delta value decreases मतलब it shifted towards the TMS, मतलब shielded हो रहा है. Likewise, अगर ये bromine है, so it directly contact with the proton, so bromine all electron pull towards itself. थोड़ा दूर है तो इलेक्ट्रॉन पुल करने में थोड़ा प्रॉब्लम होगा, और थोड़ा दूर है तो और प्रॉब्लम होगा. So as bromine is insufficient in this case to pull the electron density of this proton, ultimately this proton is remain shielded. समझ आ रहा है? अगर जैसे ये ब्रोमीन है वो इसकी इलेक्ट्रॉन पूरे पुल कर रहा है, ये थोड़ा दूर है तो उसको पुल करने में थोड़ा एनर्जी लगेगा. दिस प्रोटॉन इज और थोड़ा दूर है तो इट विल रिक्वायर मोर एनर्जी टू पुल द इलेक्ट्रॉन टुवर्ड्स इटसेल्फ. जैसे इलेक्ट्रॉन पुल करने में इनकेपेबल है, सो इट विल गिव यू द जैसे इट विल बी सक्सेसफुल फॉर शील्डिंग दिस प्रोटॉन. Likewise, this हाइड्रोजन के इलेक्ट्रॉन is protecting this proton. ब्रोमीन आके वो इलेक्ट्रॉन लेके जाएगा, so it will be come into the de-shielding, it will be de-shielded and detected as a higher delta value. जैसे प्रोटॉन प्रोटेक्टेड हो जाएगा, कैसे प्रोटॉन प्रोटेक्टेड हो जाएगा? बाय it will give away from the electronegativity. So as it go away from the electronegativity group, it will be protected. Because bromine is incapable to pull this electron of this hydrogen. It will be easily pull the electron density of this hydrogen, but somewhat less to pull the electron density of this hydrogen. So the delta value is less. थोड़ा और दूर हो जाएगा, so it is incapable to pull the electron from this hydrogen. So ultimately it is also a delta value. So if you want to shift the delta value of a particular compound, you can replace or you can add some of the group in between that electron in the electronegativity and original group. So you can shift your delta value towards the TMS. Okay, so if we add here CH2, our delta value shift towards the TMS. If we add more another CH2, it will be shift towards the TMS. जैसे इसमें और एक CH2 ऐड करेंगे तो इसका वैल्यू और थोड़ा कम हो जाएगा, towards the TMS चला जाएगा, that is of less delta value. So we can say the effect decreases with increasing the distance from the electronegativity atom. The effect completely vanish at the 4 bond from the electronegativity atom. Like जैसे ये 1 bond away है, this is 2 bond away, this is 3 bond away. उन्होंने बोला कि अगर जैसे 4 bond away हो जाता है, so that is unaffected by the electronegativity group. So consider here CH2 है और ऐड करेंगे, so that CH2 will be completely unaffected by your bromine. Because 4 bond के distance पे electronegativity effect 0 हो जाता है. Like here electronegativity effect of bromine on this proton is very high. As it go away from the bromine, it will somewhat less, and here it is less, and on another side when 4 bond is there, the electronegativity will not observed. So the substitution effect, we can review that if we add more electronegativity group, Then if we add more electronegativity group, then the delta value is shifted towards the higher value. And in position of electronegativity group, it will be you can say the more distance from the electronegativity group, the delta value is less. But electronegativity value is depend upon the or you can say the limit of this is only 3 bond. At the position of a 4 bond, it will be negligible. Next is anisotropic effect. So anisotropic means space effect. So we can say this detail is there in another video, so you can get it from the description box. So this is the anisotropic effect. So consider this is your compound. This is the benzene with 6 hydrogen, 1, 2, 3, 4, 5, 6 hydrogen, and the pi electron which is there in benzene will generate a magnetic field in this direction, and this is your external magnetic field. So here we can observe that in this region the induced magnetic field is in downward direction and external magnetic field is in upward direction. So the direction of both magnetic field is opposite to each other, so we can say it is a shielded region. Why shielded? Because this induced magnetic field nullify the external magnetic field effect, so ultimately your proton get protected or shielded, so it is known as a shielded region. So when you go here, you can observe that it is a induced magnetic field का direction भी upward है and external magnetic field का direction भी upward है. So both magnetic field is having the same parallel direction, that is both upward or both downward. Then it is known as a de-shielding effect. So here both the direction of the magnetic field is upward, so we can say it is a de-shielded region. So de-shielded region is showing by the negative charge because it will be easily come into the resonance because the shield is going to be removed or your proton is not protected by your electron density. Same here. Again, when the magnetic field come back to the protein or come back to the benzene, and here, so your induced magnetic field is also in downward direction, and external magnetic field is in also upward direction. So here the both direction is different or opposite to each other, so we can say it is a shielded region. So here is our aromatic proton. Same there, which aromatic proton experience external magnetic field is in upward, and aromatic proton, that is of proton of benzene ring, also in upward direction. So both are in same direction. So we can say it is a de-shielding. Likewise B9, here CC bond is there and electron which is sharing the bond generate a magnetic field. So the induced magnetic field and external magnetic field is in same direction, so it will be observed as de-shielding. This is the aldehyde proton, which is already seen in carbonyl compound. So in carbonyl compound, that is COR, if you replace this H with R, it is aldehyde. If we replace with R, this is H, this is aldehyde. If we replace this with R, then it is ketone. So if we add an external magnetic field in this direction and this magnetic field is also in this direction, both are in the same direction, then we can say that this proton experience a de-shielding effect. Same like acetylene proton, here CC triple bond is there, which is from inner side only one bond is shown here. So consider here 3 bond is there, and the pi electron will give you the magnetic field like this, and external magnetic field is like this. So the direction of external magnetic field and induced magnetic field is in the same direction. So we can say so. Then next is a hydrogen bonding. So hydrogen bonding means involving of hydrogen in a bond. So it will be OH also and NH also. So hydrogen bonding is showing a de-shielding protons. So how to consider this is your structure of a molecule, and this hydrogen is attached to this O. So we can say it is a hydrogen bonding. So the chemical shift depend on how much the hydrogen bonding is taking place. Means the chemical shift value is somewhat dependent upon the hydrogen bonding. Means if the hydrogen bonding less than the OH bond, and reduce the valence electron density around the proton. So the hydrogen addition of a hydrogen increase the bond length. As the bond length increases, the density of the electron across is also go somewhat far away. So it can be the experience of electron density around the proton is less, and it is a de-shielded and shifted downfield in the NMR spectrum. As it is in shielded position, like this oxygen and this proton, the proton experience electron density of this oxygen. So the electron which is revolving around the hydrogen. So ultimately, if we add more here hydrogen bond, then the addition of this hydrogen bond, the distance of the electron density around this hydrogen will go far away. So the it will be less experience the electron density due to the presence of a hydrogen bonding, and it will show the spectrized shifted from de-shielded line. So we can say the addition of a hydrogen, shifted the delta value towards the de-shielded, or we can say the downfield with a high delta value. So if hydrogen bonding is increases, de-shielding is increases, and absorption is absorbed at a downfield value. Likewise, if the concentration is decreases, the hydrogen bonding is also less, or it also decreases, then it will show the signal at upfield value. So if we want the addition of a hydrogen bond and a downfield delta value, then we can dilute the solution. So if we dilute the solution, hydrogen bonding increases and the delta value is observed at a downfield value. If we want to shift the signal towards the upper field, then we can make the solution concentrate. As the solution gets concentrated, hydrogen bonding decreases and it will be observed at a upper field. And the last is your van der Waals de-shielding. So van der Waals de-shielding is related to the steric hindrance phenomena. So it is in relation with the overcrowded molecule. It is possible that some protons may be occupied sterically hindrance position. That is, the proton experience a steric hindrance effect due to the presence of a more bulkier group. Clearly, electronegative cloud of a bulky group hindering group will tend to repel the electron cloud surrounding the proton. So ultimately, the proton gets surrounded by the more electronegativity cloud or steric hindrance effect. So such a cases, proton will be de-shielded and will resonate a slightly higher value of a delta, because it's going to be a de-shielded type, and expected in the absence of this effect is considered as a van der Waals de-shielding. Then simply we can say that if the proton is a shielded position and the proton is attached to the more bulkier group, that is 3 or 4 different bulkier group, then the steric hindrance is observed on that bulkier group and the electron density get pulled away from the proton. As the proton is shielded due to the electron density, and the bulkier group pulls this electron density towards itself, so ultimately the proton protected cover is gone. So ultimately it will be detected as a de-shielded, that is of downfield region. Okay, so these are the different factors that are going to affect the chemical shift. Main is the electronegativity, inductive effect, the substitution group, that is hydrogen bonding, and then it is a van der Waals de-shielding. Thank you.